Hello, class. Welcome to the fourth lab. We haven't done some Stata work in a while, so we have some catch up to do. And unfortunately, I did have to be off campus today. So I appreciate your flexibility and your willingness to consume the material in this way. So in the interest of efficiency, let's get right to it. We have a few things we want to cover. We definitely want to do a t-test. We want to do an ANOVA, and we want to do a chi-square. These are the big ones that we've covered recently. And those are going to form the bulk of the lab today. So I have the GSS 06 labeled version open. Listen to the way I explain these commands and follow along with me. And I'm pretty confident that everybody will be able to get through this. And I'm certainly available to help if there are questions or concerns or anything that you need clarification on. So you'll remember two types of t-testing. There is a one means t-test where you compare a sample mean to a predetermined value. And then there is the type of t-test that compares two sample means. So we use some gender, we use some college examples. Let's start with the one means t-test. I want to start with the variable of education. So this variable right here should be familiar to everybody. Check out the string of commands that I just highlighted. Tab educ, right? So I'm going to tab education. Then I am going to code it for missing, right? If greater than or equal to 98. And then finally, I'm going to summarize it. Summarizing the education variable will do one very important thing. It gives me a mean. So let's run this. And you will see the average years of education obtained by respondents in this sample, 13.29. That's my sample mean. Now I'm going to use that sample mean and compare it to predetermined values. So let's go to this next command here. The way we do a t-test for one mean is very simple. We just type t-test. Nothing more complicated than that. And so what you see here, this says t-test educ equals 14. What that is doing is it's doing a t-test of the sample mean you actually calculated, which here is 13.29. And it's going to do a t-test between that and the predetermined value I just created of 14. So essentially, this would be like if you got a word problem that said the average years of education is thought to be 14. You get a sample and realize it's 13.29. Can you say with 95% confidence that it really is different or it really is less than? So let's run that command. T-test educ equals 14. A few things are going to come up. So let's go through. If you follow my mouse here, the first column we see here is observations. So that's that's our sample size. Then it gives us the mean, 13.2934. And then we get our standard error and standard deviation. Both of those would have had to be, the standard deviation is given to you in any word problem, and you use it to calculate a standard error. What's most important is what you see here. T equals, does everybody see what I'm highlighting here? T equals negative 14.6766. That's the calculated T of a t-test between 13.2934 and the predetermined value of 14. So what we see directly below that, degrees of freedom, you'll see that is n-1, right? 44,498. And you see where it says H0 here? That's your null hypothesis. So for this case, the null hypothesis is that the mean equals 14. Now, to know whether or not we have a significant finding, I want you to take a look at these three outcomes down here at the bottom. The one on the left is a one-tailed test. The one on the right is also a one-tailed test. The one in the middle is a two-tailed test. What's the one on the left specifically? Well, it's a one-tailed test hypothesizing that the mean is less than 14. On the right side, that's a one-tailed test hypothesizing that the sample mean is greater than 14. And in the middle, See where it says exclamation point equal sign? Exclamation point in Stata is the international sign for does not equal. And how do we know if we have a significant finding? Well, we'll have to look at the probability value. So let's take a look. This one-tailed test hypothesizing less than. See how that PR value, that's what's known as your probability value. It is the likelihood of getting this result, getting this sample mean, if the actual value actually was 14. So think about this like your alpha level. It says 0.0000. That means it is highly significant. So what we're looking for, listen really carefully here, what we're looking for is a value in this PR area that is less than 0.05. So whatever your alpha level is, it's compared directly to that. And if what you see is less than the confidence level that you've set, your set alpha level, you reject the null hypothesis. So I can see not only is this finding significant on a one-tailed test that the mean is less than 14, it's also significant in the more conservative two-tailed test. Notice how the probability value is 0.0000. That does not mean the probability is actually 0. It means that this is significant beyond even the 99.9% confidence level. So the actual value that would show up here, it's less than 0.0001. We're going to go ahead and say that is highly significant. Now over here on the right side of this, where you see probability value equals 1, now that 1.0000, that is far greater than 0.05. Therefore, if you were hypothesizing that the mean is actually greater than 14, I don't know why you would do that based off the sample mean that you drew, but there's no support for that. There's actually a 100% chance, by and large, of getting this value if there was, of getting a value like this, if, the mean, oh, pardon me, I'm sorry. Sorry, let me start over. That 100% essentially refers to that you cannot reject the null hypothesis. You fail to reject the null hypothesis because that value is not less than 0.05. What would this look like on the other side? Well, we can do a t-test for education equals 12. So now the predetermined value is 12. The sample mean is still going to be 13.29. Let's see what changes with the t-test. Well, notice how now the mean, the standard error, and the standard deviation is identical, but the t-value here that you see, much different. It's because it's a different comparison. Now instead of, like in the t-test numerator, instead of 13.29 minus 14, now it is 13.29 minus 12. So we've actually gone significantly lower. And notice how the probability values have changed. If we have a one-tailed test hypothesizing that the sample mean is less than 12, we have no support for that. But we can reject the null hypothesis in situations where we hypothesize that it's different from 12. It turns out it's quite different from 12, and specifically greater than 12. So we reject the null hypothesis and conclude that the sample mean really is greater than 12. And in order to do that, right, let me refresh everyone's memory, we look at this probability value. The one on the left is a less than hypothesis one-tailed test. The one on the right over here, if you follow my mouse, is a one-tailed test greater than hypothesis. The one in the middle is a two-tailed test that simply hypothesizes a difference. That's one mean t-testing. Moving on to our two means t-test. Now I want to use the sample to calculate submeans. means. So I might get a sample mean for women and a sample mean for men. What I'm going to do instead, we used a lot of gender examples. I just want to do something different. I am going to copy and paste this entire variable creation that we've done before, where we created a dichotomous variable with only two outcomes. People either had a college degree or they didn't have a college degree. So to do that, I make use of this degree variable. I code it for missing, right? If you follow what's going on here, I code it for missing to convert 9 to a period. Then I generate the variable of college. Anybody who doesn't have a college degree, I assign them the value of 0. Anybody who does have a college degree or greater, I assign them the value of 1. Then I label it, right? Don't forget that whole thing. And this is what I end up with, right? So I ran all of that together, and now I have this nice, pretty college completion variable, below college and college degree. Let's do a t-test with that. I'm going to run through a couple here. And also as well as a mistake that I want to show you to see what would happen. Let's do age wed. So I am going to tab age wed, and I can see, actually, you know what? Not tab. I want to summarize it. So this is age at first marriage. I am curious. Do you think that there's a connection or a relationship between whether or not one finishes college and the age at which they get married? Well, most demographers believe that yes, there is. And generally speaking, people believe the general hypothesis is that people who go to college and finish college get married at a later age. Okay, well, now we have a dichotomous variable, one group that's been to college and one group that has not. So what we can do here is get an age at first marriage for people who have been to college and an age at first marriage for people who have not been to college. And to do that, we're going to do t-test age wed. So that does a t-test of the age at first marriage variable. Then I put a comma, and I do by, and that's the variable that's going to control and create the submean. So by college means it creates a mean for each group within the variable of college. This only works if I'm using a variable that has 2 and only 2 categories. So you can use this college degree variable and create it yourself. You can use the sex variable. A variety of things can be created here. But let's take a look at that. Now, the output looks a little bit different. Now, I can see, looking at my means here, right? So everybody follow my mouse. The average age at first marriage for people without a college degree is 22.86. The average age at first marriage for people with a college degree is 24.76. And you see to the right of it, each sample means standard error, standard deviation. I look at my calculated t-value and I see negative 4.6267. What that is doing is it puts, remember the discussion about sample means, X bar 1 and X bar 2, which one do you put? Stata always puts the first group first and the second group second. So this is below college minus college, right? It starts with the first group that's below college, and the second group is people who have been to college. So is there a difference between these two groups? Well, let's first look at the two-tailed test. The probability value, 0.0000. Highly significant finding, highly significant finding. So if we were doing a two-tailed test, we would say absolutely there is there is a difference in terms of age at first marriage. And so in terms of the left side of this, notice how that probability value is also below 0.05. It's because the t-test here sets up the hypothesis that those without a college degree have a lower or a younger age at first marriage than those with a college degree. That's the hypothesis that's being tested, that group 1 is less than group 2. Over on the far right side of the output here, that's where you test the hypothesis that group 1 is greater than group 2. Because group 1 has at 22.86 and group 2 is at 4.76, there's absolutely no evidence to indicate that group 1 has a greater value than group 2. That's just not the case. So looking at those two values and looking at how that t-test comes out, we can't argue that there is a positive difference here. We can argue strongly in favor of a one-tailed test with a less than hypothesis. Like, can you say with 95% confidence that those without a college degree have a younger age at first marriage than those with a college degree? All right, hopefully that's making some sense. When you run this, you would simply look for the two-tailed test in the middle, the one-tailed test with the less than hypothesis on the left side of the screen, and on the right side of the screen, a one-tailed test with a greater than hypothesis. Let's take a look at age at first marriage by degree. Can we do that? Degree is the variable that we actually use to create the college variable. Let's run that and see what happens. And you got an error message. Why? Well, the degree variable has 5 different categories. We cannot use that for a t-test. A t-test is 2 means and 2 means only. So last one I'll show you. T-test, age kid born, comma, by college. I'll run that. And now I'm curious if there's a difference in age that you have your first child, whether or not you've been to college or not. Now, generally speaking, most would argue that those with a higher level of education, and specifically those who have finished college, are likely to have children at a later age. That happens in many countries, actually. And so I can see here, let's look at my means, my standard errors, and my standard deviations. The average age of first childbirth for those with less than a college degree is 22.81. And the average age of first childbirth for those with a college degree is 27.5. That's a pretty big difference. And you can see the calculated T here is negative 17. It's a very high value of T. So because of the organization here, we are testing the hypothesis. This is the below college mean minus the college mean. Below college is X bar 1. College is X bar 2. So can we say with 95% confidence that those without a college degree have a lower age at first childbirth than those with a college degree? Well, take a look at my p-value. Highly significant. Just to reinforce this. If that value that I've highlighted, the PR value, which stands for probability, if that value is less than 0.05, we have a significant finding. Obviously, the two-tailed test is also highly significant. You see right there in the middle. And the one-tailed test that hypothesizes a greater than hypothesis, right? Those without a college degree have a higher age at first childbirth. No support for that whatsoever. All right, that's t-testing, more or less. I'm happy to answer questions about that on Monday. Hopefully everybody catches up by then. Let's take a look at ANOVA. ANOVA is a simple command here. Now we can do things across more than 2 groups. So what I want to do here is I want to look at marital status. And so what I need here is an interval variable to be my dependent variable, and I need my categorical variable to have 3 or more categories. So let's take a look at marital. I want to clean up those NAs because that's missing data. So replace marital equals period if marital equals 9. I have to take care of those missings, otherwise it's going to create a group that makes no sense. So 6 changes to missing. Now there's a really simple way to do this is to use the command one way. All that means is it's a one-way ANOVA, because there are 2-way ANOVAs and other types of ANOVAs with bells and whistles. But what we learned in class was a one-way ANOVA. So one way is the command. So I do one way, then I put my dependent variable, and then I put my independent comma, tabulate. So let's run that. I always put the thing you're getting means of first and the thing that is the grouping variable second. So what we're hypothesizing here is that average years of education is different across marital statuses. I think that's a reasonable thing to hypothesize. So one way, EDUC, marital, comma, tabulate. And look at what you have. You have an analysis of variance. Here's my, in this column, if you follow my mouse, that's my between group sum of squares and my within group sum of squares. Just to the right of that, I have my between groups degrees of freedom and my within group degrees of freedom. To the right of that, I have my mean squares, and then I have my F. So you see how everything kind of goes together here. And then finally, is there a significant finding? Yes, because that probability value that I just highlighted is less than 0.05. So this is a highly significant finding across these 5 groups of marital status: married, widowed, divorced, separated, never married. I have a highly, highly, highly significant finding. A way to add a little more detail to this would be to use the PW mean command. All that stands for is pairwise mean. What that does is it tries to use the logic of regression to understand which group's mean actually differs from the other group mean. Like what's really driving the issue here. So if we run that, you'll get a pretty serious table here, and it's the difference in sample means between all group pairings. And so you can see which are significant. So there's a very big significant difference, right? You look at the probability value right here. This is a highly significant difference between people who are widowed and people who are married. But the difference between divorced and married, that's not significant. So those group level means they don't differ from each other. Those groups don't differ from each other enough. Separated versus married, that is a significant finding. So on and so forth. So this will allow you to see which of your group comparisons are actually causing a significant statistical finding. So yeah, let me actually show the one-way command again, because that's what's most useful. Sum of squares in the first column, degrees of freedom in the second column. Mean squares is sum of squares divided by degrees of freedom. And then F, that's simply your mean squares divided by each other, right? All I would do for that is 223.859 divided by 10.235. And that gives me my finding. All right, hopefully that makes some sense. Last thing I want to look at is a crazy ANOVA where you probably are like, what would this look like if it wasn't significant? Well, I'm going to first use the child's variable, and I actually want to use that with the zodiac variable. This is why I keep the zodiac variable around, because I always want something that isn't really going to be significant. So here's my hypothesis. People with different zodiac signs will have different averages of number of children. So I code that number 9 for missing. And now I'm going to use that over the 12 categories of zodiac. Actually, I think I need to code that for missing. Yes, I do. All right, let's take care of that. And now let's run our one way. Look at how high that probability value is. I have essentially no between group variation, and all the variation is happening within the group. Therefore, there's a lot of noise in this data set, but none of it is driven by the group level differences. How do I know that? Well, my calculated F here is 0.2, very tiny. And my probability value, much, much greater than 0.05. So I would have to look at that and find 0.05 or less, right, as my probability value in order to reject the null hypothesis. And lacking that, I now have to conclude that, yeah, there is no difference across zodiac signs in number of children. Let's take one more look at one. education by religion and tabulate that. Oh, actually, now we have a significant finding. Despite the fact that I did not code for missing. But that's, you would have to go do that. Either way, there's actually a ton of within group and between group variation here. The F test is 7.09 and the probability value 0.0000, far less than 0.05. And that tells me with well over 95% confidence, I reject the null hypothesis and I conclude that there is a significant association between one's religion and the number of years of education that they obtain. So yeah, that's a t-test, and that is that's ANOVA. That's all that's going to be on the upcoming homework. So I am not going to actually go any further and do chi-square. We'll fold that into the next lab that we do, where we do chi-square and correlation. That'll give us something to work through on that. So yeah, again, I apologize for doing class in this fashion. I'm happy to go over this with anybody next week. And thank you for your flexibility. It's really very much appreciated. So yeah, thank you. Have a great rest of your day. And if this was actually, after you watch this, if this was completely confusing, why don't you just shoot me an email so I know. If you generally got it, shoot me an email so I know that one as well. Thank you. Bye.